Hi everybody! So today we're going to explore the experiments you can do with the Limonite after Pyrite kit from Snellius Minerals. This is our first video about pseudomorphism. Pseudomorphism occurs when a mineral replaces a different mineral, however our new mineral retains the form of the old mineral. This can either give us information on the history of a sample, but can also cause some confusion if we don't identify that pseudomorphism is going on. The word pseudomorph in Greek means false form. In the case of limonite after pyrite, pyrite was our original mineral. Our original pyrite has been replaced by limonite, and our limonite has retained the form of that original pyrite, even though limonite belongs to a completely different crystal system than pyrite, and so would actually crystallize in a completely different form if left to its own devices. You can pick up one of the limonite after pyrite kits from the eBay store Snellius Minerals if you'd like to follow along. And the kit consists of a cube or nearly a cube of pyrite and a cube or nearly a cube of limonite. There's a bit of wiggle room there, but you'll get the idea of what's going on. First, some relevant information about pyrite. Our pyrite is iron sulfide, FeS2, and our pyrite crystallizes in the isometric crystal system with the point group of 2/m 3 bar. So let's take a closer look at our pyrite and limonite samples. As our pyrite crystallizes in the point group 2/m 3 bar, this point group symbol lets us know that there are going to be three twofold rotational axes with perpendicular mirror planes. These are going to be the A crystallographic axes for our pyrite. And then our pyrite will also have four threefold Roto inversion axes as symmetry elements as well. Let's rotate the pyrite sample around a bit so you can get an idea of the form and symmetry that's going on with our pyrite. You can also see the bright, brassy, metallic luster that's characteristic of pyrite as we rotate this around a bit. This luster is why pyrite is known as fool's gold. Because it is so metallic and yellow, sometimes people do mistake this for gold. Now let's rotate our limonite pseudomorph after pyrite so that you can tell, hey, these are pretty much the same shape. Our limonite and pyrite are pretty easy to distinguish from one another except for the shape. The limonite, of course, is dark brown and has an earthy luster, very different from the metallic brassy luster of our pyrite. Let's investigate the symmetry of our pyrite in greater depth. And here we actually run into a bit of a complication with the form our pyrite displays and the actual point group symmetry of our pyrite. The cubic form that we see has a symmetry of 4/m 3 bar 2/m. But the true point group of our pyrite is 2/m 3 bar. The reason for this discrepancy is that what we actually need is a form that is more complicated than the cube in order to truly show off the point group symmetry of our pyrite. This is an issue in many of the crystal systems where you can have a mineral of a less symmetrical crystal class actually masquerade as a more symmetrical mineral, because what we really need is a form that cuts multiple crystallographic axes at different lengths of those axes in order to form something really cool like a pyritohedron. However, many pyrite cube specimens actually have a feature that allows you to distinguish that what we're seeing here is a twofold rotation axis and not a fourfold rotation axis. And striations on the cube faces of our pyrite crystal can help us to make this distinction. In this example, our pyrite cube doesn't actually have any striations. However, we can see the traces of these striations in our limonite pseudomorph after pyrite. Long story short, what we're actually seeing here is a twofold rotation axis for our pyrite. This axis is perpendicular to a mirror plane and runs from cube face to cube face in our pyrite crystal. Once we've spotted one of these twofold rotational axes, we know there must also be two more of these going from cube face to cube face in our sample. And our three twofold axes with perpendicular mirror planes are going to be our A crystallographic axes for our pyrite. So in addition to our twofold axes with perpendicular mirror planes, we also are looking for 4 threefold roto-inversion axes. And let's take a look at our pyrite in a different orientation in order to spot these. Our pyrite cube has 8 corners, and our threefold roto-inversion axes lie from corner to corner of our pyrite cube. And you can tell these are actually threefold roto-inversion axes and not just threefold rotational axes because of the relationships of the cube faces we see and the cube faces below. We go into a deeper dive explaining threefold roto-inversion axes in the video Calcite Crystallography, which I'll link to here. So here is the appropriate symmetry symbol for our threefold roto-inversion axis. Once again, there are 8 corners to our cube. Each of these axes runs from one corner to another, and so there must be 4 of these threefold roto-inversion axes in total. Special bonus symmetry item. Even though the striations on our limonite after pyrite cube aren't that distinct, if we highlight the pattern that the striations display, they do an excellent job highlighting that threefold roto-inversion axis. Alright, so we've checked out our form and symmetry of our pyrite, and we've seen that our limonite pseudomorph after pyrite effectively steals that form. What morphology would limonite take on if it didn't have pyrite as a template? So here's an example of one of the common habits of limonite, and this is a bit different than what's going on with our pyrite. Our pyrite we were actually looking at before is a single crystal. Here our limonite specimen is actually made up of many small crystals arranged in these spheroidal aggregates. So this is actually more a habit than necessarily the form of a single crystal. And depending on who you ask, this habit would usually be referred to as either botryoidal or mammillary or perhaps reniform. You can get a better idea of how this material grew in layers over time with this side view of the sample. And now I have to tell you a terrible secret, and that's that limonite isn't actually a mineral. Limonite is a field term for the many iron oxyhydroxide minerals that occur together in complicated aggregates. These minerals include things such as goethite, lepidocrosite, and ferrihydrite, in addition to others. So the term limonite is a bit squishy. We'd think about it as this amorphous aggregate of different phases. And so the overall chemical formula of our limonite is also highly variable. However, for simplicity today, we're just going to use the chemical formula of goethite, which is often a primary component of limonite anywho. So what's going on that our well-formed pyrite crystals are being replaced by this amorphous mix of limonite? Time to break out the chemistry. So what you see here is a simplification for understanding how we get limonite pseudomorphs after pyrite. Our pyrite, iron sulfide, is unstable at the surface conditions of the Earth due to the presence of oxygen and water. And so when rocks bearing pyrite begin to be exposed to oxygen and water from the surface of the Earth, they start to weather. This chemical reaction takes our pyrite and combines it with oxygen and water in order to form sulfuric acid and our iron oxyhydroxide, our limonite. So under the right conditions, our limonite actually just replaces our pyrite cube in situ. Sometimes this reaction doesn't go to completion, and so you can also find pseudomorphs that still have cores of pyrite. Here's an example where you can see a bit of the pyrite still remains in the interior of this pseudomorph. It's definitely not as shiny as our pyrite cube, however, as it's been through a lot. So this should give you an idea of how we get our limonite after pyrite pseudomorphs. You may have also heard me say sulfuric acid earlier. And if you thought to yourself, well, that doesn't sound good, you'd be right. So one of the problems that occurs when rocks bearing pyrite or other sulfides are mined extensively is acid mine drainage. And this is caused by the oxidation of those sulfides and the generation of sulfuric acid. That's a topic for a different day, but note that the same chemical reaction that gives us our nice limonite after pyrite pseudomorphs also generates sulfuric acid, which can be an environmental hazard. To wrap things up, today we took a look at the Limonite after Pyrite kit from Snellius Minerals. We talked in detail about pyrite and also examined its symmetry, form, and crystallographic axes. And then we investigated limonite, which isn't a mineral but a field term for a complicated aggregate of iron oxyhydroxides. The key to understanding how we get our limonite pseudomorphs after pyrite is to actually look at the chemical weathering of the mineral pyrite at the surface of the Earth. Our pyrite ends up reacting with oxygen and water in order to form sulfuric acid and limonite. So when we find our limonite after pyrite pseudomorphs, we end up learning something about the history of our sample, primarily that conditions favorable to the formation of pyrite must have existed at one point in time. So thank you for watching this video. If you'd like to pick up a limonite after pyrite kit, you can do so at the eBay store Snellius Minerals. And if you have any questions, comments, concerns, or specific requests for me, feel free to reach out at the email snelliusminerals@gmail.com. Here are the references I used in the creation of this video. Thanks again for watching, and have a great day.